just to recap what we have done last time, so let's just take a look at this frozen lake game. So this is a famous one, which you have in play with this guy a couple of times in the assignment. Let's take a look at this and see how we can define those components here. So if you play frozen lake, here in this game, you have one player. So this is your agent. And there is a 4x4 grid. What you want to do, you want to get to the end point, right? You want to get the prize. And this is quite simple, of course. I mean, you can just move towards that. But the point here is that each time that you decide to move, so for instance, if the agent wants to decides to go to right, there is a chance, I mean, with probability 1 minus p, this is going to go to the intended direction, but there is a tiny probability p, and with that one, it could just slide to another direction. So for instance, when you are here, if you just press right with probability, I don't know, say p is 10%, then with probability 0.9, you are going to get to the next cell. But with probability 0.1, you might either stay here or just slip down, right? So stay here when you is like moving towards up, right? And then since there is nothing up, then you stay here. Same thing going to happen like here, right? So if you are here in this cell, then eventually, if you just press right with probability 0.9, you're going to go right. With probability 0.1, you might go any other direction, right? So this is the game. And obviously, you can see that there is no guarantee that you are going to definitely win. But you can guess that when p is very small, then when you play it by simply going towards the prize, you are going to win most of the times, right? So if you keep on going and you get to the prize, you're going to get a reward. If you get to any of these shallow cells where there is a hole, then you're going to lose, right? So you're going to get a negative reward, right? And now if you want to formulate this guy, reinforcement learning problem, then first of all, you need to specify the state, action, and reward, right? So what is this state? Any guess about the state? How should I define the state? Yeah, go ahead. Yes, the cell that you are playing in, right? So the cell that you are in is going to be your state. So you have state 0, 1 till state 15. You have 16 different states. Depending on which state you are in, then you just need to know the action, right? You know the action. Then you can describe what's going to be the next action and what's going to be your reward, right? Because the game is going to explain you how this is happening for the next state. So this is your state. Your state is basically the cell that you are in. What is the action? What kind of actions you can do? Is any of the direction that you can move, right? So in general, you have 4 actions wherever you are, right? So I'm going to show them in this form. So I'm going to say if you want to go left, three, okay? So it's counterclockwise. Yeah, go ahead. It's a part of environment. It's a part of environment. It's a part of rewarding system. Yeah, but you are thinking about the end of the game, right? When you lose, for instance.
Yeah, I'm also just thinking like, what parts of the environment are you trying to represent in your states? Like, what is
the information that you need in order to explain your next state and reward, right? The thing that you are thinking about is like you fall in the shallow cell, right? Yeah. Or you get the prize. They're going to be described by the reward and the change to the next state. And I'm going to explain it. Actually, purposefully I put this example here. Yes? Yeah, this is the one that I told you. So you could formulate it differently. You can say that when you are here, you have only 2 actions, either go right or down. This is one way of thinking about it. Here you have all the actions, but if you do the action above, say that right now you don't have any sleeping, okay? So you just press and it goes. When you push up, then you're not going to move. So your state is not going to change, right? So the transition from state 0, when you act, here up is 3. When you act 3, is going to remain 0, right? So you can explain that way. This is a more concrete way of explaining, right? Because playing with, working with an action set which is changing depending on state is harder, right? Questions? No question. Okay. So this kind of action, and finally, it's reward, right? So if you fall into any of the holes, then you got one. In another cell, the game is ongoing, so the reward is simply 0, right? So you can formulate it in this form. So you would say, my reward is coming again from a discrete set, so I have 3 rewards, -1 when I lose, 0 when the game is in, +1 when I win, and then again, given the cell, you can say what is the reward, right? So if you know the cell that you are in, if you know the action that you want to do, you can explain what's going to be the reward after doing that action. Everybody's clear? Okay, so now, the rewarding system here is simple to describe. It simply explains how you're going to get your next reward. So if, for example, you're in cell S, this is your state, and you do action A, you just decide one direction to go, then you might go in the intended direction, right? So you press right, you go right, right? The chance of going right is going to be 1 minus p, right? So the chance of getting the intended reward, the reward that you expected to get when you move, this is going to be 1 minus p. The chance of getting another reward, p, sorry. Yes? So this is the direction that you are going. So with 0.9, you're going to get the reward that is there. So if there is a frozen cell, then it's going to be 0. If there is a hole, it's going to be -1. And with probability 0.1, you can get any of the other rewards, right? Okay. This is the rewarding system. The transition system, you can again explain it the same way. So you can say, when I am in particular cell S, if I decide for action A, then with probability 1 minus p, I'm going to get into the new cell, which is, again, describing the next state. Or I can sleep to another state, which are around it, and then the chance of getting there is, again, p, right? So you see here that both transition and rewarding system, both of them are random, right? And this is simply because of the environment, because the environment is behaving random. Okay, so that's it. Here is one particular example. For instance, say we are in this particular cell. So this is a state 4 because 1, 0, we start from 0, right? 0, 1, 2, 3, now it's 4, right? And here in state 4, if I want to just move in direction right, so the action right, I'm presenting it by 2. So I'm going to say that with probability 1 minus p, I am going to be at the cell 5, right? The next cell. With probability p, I'm going to be either at 0 or 8, right? Same thing you can do here. So for the reward, you could say with probability 1 minus p, the reward is going to be -1 because I'm going to fall in this hole. Or the reward is going to remain 0 with probability p if it just slips to any other direction, right? Okay, so one thing that your friend also mentioned, so what if we get here, right? So when we started with modeling, I told you that you think that you are going to play this game forever, right? When it starts, it never ends. T goes forever, right? And then this one, when you play, at the end of the day, when you get here, you lose, and the game is over, right? Now, the question is that how we can impose this condition on the problem. Since we have a state, we can use the notion of terminal state. This is going to make story much easier. So we can define what we call a terminal state. What is the terminal state? It means that when you got there, then it doesn't matter what action you do, you're going to remain there forever, right? And it doesn't matter what your action is, you're going to always get reward empty, 0, right? Nothing going to change. You do any action after that, nothing changes, right? So here, for instance, what I can say when the game is over. So after getting 5, doesn't matter if I just press any direction, I'm not going to get out of it, right? So I'm going to remain in cell 5 forever, right? So this is the terminal state, right? And the reward is the same thing, right? The reward going to remain 0. So I can play the game. I'm going to get probably 0, 0, 0. Then I get the reward minus 1. I lose. And after that, I'm going to, again, collect 0, 0, 0, 0 forever, right? Which is OK, right? It doesn't change anything. But this makes us get rid of the notion of time, right? The time now, like terminal time. The time is going forever now, right? Because you might play the game and it ends after 2 steps. You might play this game and it ends after 10 steps, right? So you don't want to get into that trouble. This terminal state is going to resolve the issue. Everybody's cool? So the terminal state is essentially the state that when you got into that state, regardless of the action that you are doing, you're going to always transit to the same state. So it's a kind of state just remaining in itself. And the reward that you're going to get is going to be 0 afterwards, right? So you collect it up to that point. You don't collect anything after that. If you start playing this game, so you start with some cell, you play, and then you end up with a terminal cell, right? And then when you get into that terminal state, then the game is over, right? Now, if you want to continue playing, you need to start again from scratch, right? So this trajectory from very start to the terminal state, this is what we call it an episode. I thought I have it here. Oh, I don't have it here, right? Okay, I have it in the next slide, sorry. But the trajectory that you start and you end at the terminal state is what we call it episode, right? And then when we go further, you're going to collect so many episodes because you want them as samples to start learning what is the value function, what is the policy function, okay? Now, one key factor here about the terminal state is that if you get here in the terminal state, what's going to be the rewards that you collect afterward? It's going to be 0, right? So what is the value of this state? It's going to be 0, right? And it doesn't matter what your policy is, right? So whatever the policy you play with, once you get into the terminal state, the game is over. Whatever you do after that, you always collect 0, so the value is 0. So this is a natural property of the terminal state, that it always has a 0 value. You can simply see it by writing down the formulation. So you would say, OK, I want to calculate the value given the policy that I have in this state S. This state is a terminal state, right? So I'm going to say that this is going to be the expected return that I'm going to get given that I am in this terminal state. And the future return, I can write it down in this form, right? Immediate reward, second next reward, and so on, right? Now, the immediate reward is 0. The next one is 0. Anybody after that is 0. So all of them add up to 0. This future return going to remain 0, and the expectation of 0 is always 0. And it doesn't matter what is your policy, right? So this is a kind of natural property of your terminal state. When the game is over, you're not going to collect anything anymore, right? Everybody's cool? Yep. Sorry? Oh, no. In this notation that I have, that one was RT. Yes. Yes, exactly. So you get into this state, then you do an action, you collect a reward, right? When you got into the terminal state, that value that you are talking is the value of the previous state before you get into this stage, right? So everything else afterward, all these other RTs, are all just 0? Are all 0. You got into the game is finished, right? then after that, whatever you press, nothing going to happen, right? So you're going to collect always 0, right? And you remain in the same stage, right? Yeah? Yes? Yes, yeah. In this example, yes, yeah. For this setting, exactly. Questions? No question? Okay, great. So, yeah, here is episode. So episode is the trajectory that you from your starting point towards the terminal state, right? Then if you play the game multiple times, essentially you collect multiple episodes, and later on we can use it to learn what the value is and what is the optimal policy. Okay, so now for this particular game, the Frozen Lake, the policy is essentially, you think of that pi a given s, it's essentially the direction that you are going to play at every cell, right? So for instance, you would say, okay, if I am here at this particular cell, I'm going to move here. Then you could say that pi of the direction that you do, given the state 0, is going to be only only right, right? So only right happens with probability 1. Anything else is happening with probability 0. So here, as you see, you can have a sort of randomized policy. Because here at this point, at this particular cell that you see 2 arrows, one of them right, one of them down. So this guy, I am saying that with some chances I go down, with some chances I go right, right? So it's a probability distribution. I say when you are at this cell, s equal to that cell, the action of right happens maybe with probability half. The action of down happens with probability half. But I would never go left or up, right? Everybody's clear? Okay. So this is the policy that you have, for instance, for this action 2, which is right, then it's going to happen with probability 1. Any other action happens with probability 0. But then for that particular cell 9, you could have 2 different actions, right? You could either go right or down, right? And they happen, each of them with 1 probability, right? So now, here, if you are talking about the value of every single cell, so you should look at this point and see that when you play with this policy, what is the average? Like you play with this policy thousands of times. Each time you are going to collect 1 return. And then the average, the expectation of those returns is going to be your value for every single cell, right? So, for instance, say I have p equal by 0. Okay, when p equal by 0, it means that there is no slip. Okay, wherever you want to go is going to go, right? Now, if that is the case, then if you play with this policy, you're always going to win, right? Because at any cell, you are just moving toward your prize, right? And there is no chance of slipping. So this is essentially the optimal policy, right? And then when you play with this optimal policy, you always, no matter which cell you are in, you're going to end up collecting reward 1, right? Now, if you think of discount factor to be simply 1, then wherever you're going to collect 0, 0, 0, 0, 1, the game is over, right? Again, here, it's going to be, I don't know, 0, 0, either here or here, 0, 0, 1, and the game is over, right? So at any state that you are, if this is not a terminal state, you are going to end up with 1. If this is a terminal state, you're going to end up with 0, obviously. And then this is going to be your value function when the probability of slipping is simply 0, right? Yeah, you can. Gamma equals by 1, yeah. Everybody's clear? So value of every single cell for this. But if I play with another policy, so if I play with policy that when I'm here, I decide to go right, then at this particular cell, whenever I get here, I end up losing. And then the reward always for that particular cell is going to be -1. So the value of that cell is going to be -1, given the policy that I'm playing, right? Now, the policy that is going to maximize this value set, this value function, is going to be your optimal policy. And obviously, this guy with no probability of sleeping is going to be optimal policy, right? Because you're going to always win, and this is the best thing you can collect in this game, right? So if you have p equal by 0, this guy is going to be your optimal policy, right? Okay, cool. Questions? Yes?
We don't need to stick with the same policy throughout the game, right? I'm not talking about the hybrid policy, but like with respect to time. Say like from time step 1 to 10, we play with policy 1, and then starting from time step 11, it's policy 2.
You can do it, but then the issue is with the notion of time, I guess. Because, well, I mean, even in that case, you can say that, I mean, your policy is then not a kind of constant on any stage, right? So it also depends on time. You mean like 8, this is going to be pi of A, S, and T. You can play that, but the point is that what is the benefit out of it? No, there is no benefit, I guess, out of it, right? Because if you want to change, it's only possible, there is only possible benefits when you do know that your environment is also going to change through time, right? But that is not the framework that we're right now working with, right? So these are two different things. You sometimes have adaptive system, right? Like some physical rules are valid when the system is in the stationary status, but when it's in the transition status, the dynamics change, right? And then if this is the case, then your system is essentially described with two different set of equations, right? And then your environment is changing. Of course, your policy should change as well. But in these settings that we're talking, at least right now about, is that your environment is fixed through time. It's not changing, right? And any of those weird behaviors, we are somehow incorporating it inside the randomness of the environment, right? So in that sense, anything that you are thinking about somehow lies within the randomness of your policy, right? Yeah. Yes? To the holes? Your question. Okay. Yes, you're going to change it because if this is 0, for instance, the reward is going to be the same as the case where the game is ongoing, right? And then there is no intention for your agent not to lose, right? Like here, for instance, right? If your agent would go right because it doesn't want to go down and lose, right? Because when it goes down, you're going to get reward -1, right? But if it's going down and getting reward 0, then what is the intention for your agent? You only mean that your agent might be interested to just keep on going to get +1. You keep the +1. Yes, but you're going to make your agent less sensitive, right? If you make it a minus, locally it's going to always avoid it, right? If it's only looking. But long term, yes. I mean, theoretically, the algorithm, if it converges for this one, it should converge for that one as well. That's correct, yes. Obviously, but for a general case, I mean, obviously, as long as the behavior of the reward is not changing, it should be the same policy. That's right. But in your case, you're just somehow you use it like you're doing it on a borderline, because you would say, I do have the, I guess it shouldn't change in general. That's right. Yes. Yeah, you had a question. To get 1, right? Yeah, yes, that's right. This is why I said, like, if you got Gymnasium. Gymnasium is a quite well-known API that people use to implement an environment. So you can simply install it and use it in Python. So you can just import it, and then you can either define your own environment. So you can build a custom environment there where you just describe the rewarding and transition system inside the environment. And there are a bunch of well-known environments, like, for example, the card pool, the frozen lake, the mountain car, these things that we use in the assignments, and we also use them in the, some of you might use them even in the project. So you can use them already available, so you don't need to implement it from scratch. So next Tuesday is the first tutorial, and Isan is going to just overview on this Gymnasium. He tries to just do one custom environment and also use one available environment there, so that you see how you can use Gymnasium. So this is one screenshot, for example, of a very basic one, the frozen lake. So what you can do, you can essentially import the Gymnasium, and once you import it, then you can just use all of the functional operations that are defined there. For example, here you make the environment first, so the frozen lake is already available there, and then you just first reset your environment, so you start from the state 0, and then you can just put different Boolean parameters there to just control the environment, right? But the key point here is that you do your action, right? So you just sample one action from the environment action space. It means like 0, 1, 2, 3, right, in your case. And you just sample one action, one of the action coming out. This is just randomly sampled because we are just playing random here. And then what you're going to do, you're going to just give that action to the environment to just do one step, right? And then you're going to change to the next state. It's going to return you a reward, right? And you can keep on playing like this, right? So it's going to make life much easier, like exactly what we are talking about in this course. You can just do it with a few lines of codes there. And it's a quite, solid and robust environment that you can use for programming. Okay?